In this video, we're going to take a look at integrals. But before we look at integrals, let's talk about Riemann sums. A Riemann sum is an approximate of the area between the curve and the x-axis. And of course, an integral is going to give us the exact value. The approximate is going to be an overestimate if you have an r-ram on an increasing function. So here's an increasing function, and an r-ram is where the rightmost corner intersects the curve. So your rectangles will have this little bit of space above the curve. Now, you'll also have an overestimate on a decreasing function with an L-ram. And so this guy right here, you can see we have a decreasing function. This time the left top corner intersects the function. And so again, you have these little bits that are above the curve. The approximation is an underestimate if you have an R-ram and a decreasing function. So here's the decreasing function with the rightmost corner intersecting, and you see we have these little bits of orange that are under the curve, or on an increasing function with an L-ram. So again, you have the little bits under the curve. When you find an L-ram and an R-ram from a table, it says if you are finding a left sum, you will use the first y value for the first rectangular height, and the last rectangle will be the next to the last y value. If you're finding a right sum from a table, you'll use the second y value for the first rectangle height, and the last rectangle height will be the last y value. Riemann sums approximate the area between the curve and the x-axis, whereas the integral is the actual area. So here's a couple of examples. The first one says, use a left Riemann sum to approximate the area from 2 to 17 of this function with 5 equally spaced rectangles. And so I can see that the base of my rectangle is going to be, and in all cases, 3 units. And so that's what this guy out here is. If you're using a left Riemann sum, you're going to start with the first y value. So it'll be 1, 5, 6, 9, and 14. Multiply by that 3, and there's the answer. There was an error on y'all's copy, so change this to a right Riemann sum. All right, so again, the base of the rectangles are each 3, but this time we'll use the heights of 5, 6, 9, 14, and 16. And then we can see there's the total. So on an integral, you have several different rules. One rule that we use is if you have your boundaries and you want to reverse them, you can reverse them and then make your integral negative. If you're looking for the area from a to a, of course, that is no area, so that's 0. If your function is being multiplied by a coefficient, you can pull that coefficient out front. If you are adding or subtracting two functions, you can separate them into two integrals. This next one, okay, so let's see, b is some value in between a and c. And so if you have the integral from a to b plus the integral from b to c, that is the same thing as the integral from a to c. And then this last one, this is just when you have an indefinite integral, you're not going to be evaluating. You don't have boundaries. You just need to do the reverse power rule and then add the plus c. And then there's some examples over here that you can look through. The fundamental theorem of calculus, there's 2 fundamental theorems. The first one just said that the derivative of an integral is just the function evaluated at the upper limit times the derivative of the upper limit. In this case, the derivative of x is just 1, and so it's just f of x. Here's an example working through, and it was incorrect on your copy, so please make the changes. All right, so first thing, we needed to reverse the boundaries because we want a constant as our lower limit and the function as the upper limit. So because I reversed them, I negated. Now we just evaluate this function t squared at 3x. So we plug in the upper limit and then times the derivative of the upper limit. And when you work it out, we get negative 27x squared. The second fundamental theorem of calculus is this one. So if you have the integral from a to b of f prime of x dx, that's f of b minus f of a. And it says to use the graph of f on the next page. If h is an antiderivative of f and h of 1 equals 9, then what is h of 2? And so I just made myself some notes. It says h is the antiderivative of f. And so I have h and then f. And so to me, in my mind, I can process this. Okay, so h is my position function, and then f will be my derivative function. That'll be the derivative. Okay, so anyway, this is just the second fundamental theorem. And so we evaluate the antiderivative at 2 minus at the lower limit at 1. And so since we're solving for h of 2, we're going to add h of 1 to the left side, and they just switch the order here. And so this is just the area under the curve from 1 to 2, and it wants us to use this graph here. And so the area under the curve from 1 to 2 is 2 units, base times height divided by 2, plus h of 1, and that was given at 9, so it's just really 2 plus 9, which is 11. When you have a function with a function inside, okay, we use substitution. So the first thing is we need to decide what the inside function is, the u. Find the derivative of u with respect to x, solve for dx, substitute for dx in the integral, find the antiderivative of the function in terms of u, and then substitute the what u equals back into the antiderivative, and then use your lower and upper boundaries of the original integral to substitute in and solve. So here's an example, and again there was a little error in the calculations here, so I've corrected. So our u would be the inside function, the derivative of that would just be 2. Solving for dx, that would be 1/2 du. All right, so where you have this dx, you're going to have 1/2 du, and this is just going to be u squared. This 1/2 is going to come out front, and then we take the we're going to differentiate. So this is going to be u cubed over 3. And if we clean that up, that's just u cubed over 6. And then we plug the u back in, and then we're going to evaluate. And so at the upper boundary, 2 times 9 plus 1 is 19 cubed over 6, and that reduces to 6859 over 6. And then this function evaluated at 1, so 2 times 1 plus 1 cubed divided by 6, so that's 3 cubed, which is 27/6. If we subtract those, we can get the answer there. So here's our next one, functions defined by integrals. If g of x is the integral from 1 to x of f of t dt, then g prime is equal to f of x, right? If we take the derivative of these two, the derivative of this is just g prime of x, the derivative of this is just the function evaluated at the upper limit, and then the second derivative is just of g is equal to the first derivative of f of x. So you're given the graph of f, and I just like to label it. Like this, I'm looking at the derivative function, and it says find g and g prime of 4. So we're going to just substitute in 4 into our g function, and so that would be the upper limit there. And so we're finding the area between 1 and 4 of this function. And so from 1 to 4, I already calculated this area was 2, and this area here is -3, so 2 minus 3 is -1. So that is what g of 4 is. Now g prime of 4 is just the slope at 4, so it is f of 4, and that value is -3. That corresponds to -3. Slope field and differential equations. A differential equation is one that is defined by dy dx equals. The small segments on a slope field represent the slopes of the tangent lines to the function at each point. When you're solving differential equations, we separate the variables, move all the y to the left, all the x to the right, separate, then integrate both sides of the equation, and then we add c to the right side. We substitute in the particular solution to solve for c, and then we substitute the value in for c and solve for y. If you end up with a plus or minus sign, you do need to plug in your initial condition to decide whether it is positive or negative. And so here's an example. Again, a little bit of errors here, so I've corrected on this slide. Your particular solution is 1, 2. So here's the function, separate. So I'm going to multiply both sides by y and multiply both sides by dx. Here it is. Then we integrate. The antiderivative of y, of course, is y squared over 2 is equal to 1 over x is natural log x plus c. Then we plug in our initial condition. E to what gives you 1? Well, that would be 0. So we know our c value is equal to 2. All right, so now we plug in the 2 for our c, and we solve for y. So if I multiply everything through by 2, to clear this fraction, that'll give me 2 ln x plus 4. Take the square root to undo the square, so we end up with a plus or minus. So check your initial condition. We have our y value is 2, and so we know that it has to be a positive because 2 is a positive value. And here's our final answer.